Welcome to the second session of the French-American Innovation Days about physical sciences and engineering applied to the environment. I am Linda Amici, Deputy Attaché for the Office of Science and Technology at the French Embassy based in Houston, working with Renaud Seigneuric, the Scientific Attaché. So the FAID are organized with the Harte Research Institute based in Corpus Christi in Texas, and with CBIOS and Mexico in France. We'll hear to Christelle Roger at the end of this session. On Monday, we had a first session dedicated to the innovation in energy, discussing the various encounter challenges. And today, the session is dedicated to the innovation and challenges in water management, coastal conservations, and the actual policy and strategy. The presentations of today are diverse from both countries and with a strong focus on biomimicry. The moderator of today is Paul Montagna, Endowed Chair for Ecosystem Studies and Modeling at the Harte Research Institute, who will give a short presentation later on. But first, let's start with an introduction given by David Yoskowitz, who is Senior Executive Director of the Harte Research Institute. David, the floor is yours.
Thank you very much. Thank you for having me kick off the second day of this Congress. Thank you to the Office of Science and Technology. I'm just going to spend a few minutes sharing with everyone that's joining us today a little bit about the Harte Research Institute and our process and how we approach things and how this can help kind of stimulate potential conversation today around the the work in water and water management. So we organize ourselves around a very unique model, especially in the coastal and marine sciences. We call the HRI model. And this, this model really brings together both the biogeophysical sciences, the social, behavioral, economic sciences, and the policy concerns in a very holistic approach. So it's not as if we're just approaching the issues and challenges that we have from only one discipline, but realizing that we need to be able to do this from all of the scientific disciplines, including social, behavioral, and economic sciences. So that's how we organize ourselves at HRI, at the Harte Research Institute. So our process is really, we're not looking for create solutions that are looking for a problem. What we want to do is our work is basic, but also very applied at the same time. So we need to understand from stakeholders, and that could be private sector, those could be conservation NGOs, those could be government sector. What are the challenges that they have? We engage those individuals to help define that issue, and then we bring our science to bear on creating those solutions. So in order to study and begin to come up with solutions to solve the problem, partner engagement is critical, right? We have a set of expertise here at HRI, but it is by no means the only expertise that we need to bring to various problems, whether it be water management, coastal restoration, looking at ocean acidification, resilience, looking at community resilience. We realize that partner engagement on the sciences as well as in the private sector and with government partners is critical in finding those solutions. And then finally, it's not just finding the solutions and handing it off and saying, good luck, take this and do well. An important part of our model is also making sure that we are part of the implementation of that solution. So whether it is dealing with government entities, whether it be at the federal, state, or local levels, helping them see through this solution into the implementation phase, also with our private sector partners, as well as conservation and NGOs. And then finally, this is really what drives the science and solutions that we want to see instituted within the Gulf of Mexico, but what we learn here in the science and solutions that we develop here, we are very open to using that around the world. In fact, many of our people, every one of us of the senior team here at HRI has worked around the world, from Paul's work in Antarctica to Larry's work in the Middle East, and my work in Australia are just a couple of different examples of that. So what we learned here, very much can be transferred to the rest of the world, and what the rest of the world is doing and how we can, apply it here in the Gulf of Mexico. We want to be part of that as well. So that's a little bit of an introduction to the process and approach that we have here at the Harte Research Institute. I want to turn it over to my colleague, Paul Montagna, who is going to be the moderator for this session on water and water management. So thank you all.
Thank you, David. I'm going to start with a brief presentation. And let's see. I'd like to start off talking today about, let's see, do you see a full screen or just partial screen?
It's a partial screen.
Yeah, okay. Let me, now you should see a full screen, right?
It's the same one, but that works.
Okay, well, anyway, I was going to talk a little bit, I was going to start out by talking about the importance of environmental flow in water resource planning today. This is a topic we've been working on for quite a long time. First, I'd like to define what environmental flows are. We really think about three different things. We think about in-stream flows, which is a flow from within a stream and within a river, and then inflow, which is flow from a river to an estuary, and then finally outflow, which is flow from estuaries out into the coastal ocean. And all of these environmental flows are very important for maintaining productivity and health of habitats in the coastal zone. But they're really different kinds of effects. Inside rivers and streams, the in-stream flow, we always think of flow itself as having a direct effect, and things like elevation drives the flow rates and the flow stage. And this creates the different habitats in which the organisms live in. Think about things like riffles, runs, and pools. In contrast, inflow going from a river to an estuary is more of an indirect effect, because the river is bringing in sediment, dissolved organic material, particulate material, and of course it's diluting salinity from the ocean, which is related to the tidal connection. And it's actually those estuary conditions that drives the resources in the coastal regions, and particularly the sustainability of habitats over time. Now, as you're probably all well aware, there's really been an unprecedented change in global hydrology. Since World War II, the number of large dams being constructed all over the world has increased exponentially. And in fact, today, we have probably 3 to 6 more times water in reservoirs than in natural rivers or lakes or the environment. So the bottom line is that we're intercepting runoff and we're changing downstream habitats. Now, the funny thing is, every developed country in the world has got really strong water quality regulation. But here in the US, only 3 states have inflow or water quantity regulations that regulate how much water should flow to the coast. And in fact, Texas was the very first state in the country to adopt such laws. And that was way back in 1985. Those laws were amended quite dramatically in 2007. And now any new water permit does require a set aside, to the extent possible, of an environmental flow regime that's adequate to support a sound environment. And we define a sound environment as maintaining the productivity, extent, and persistence of key aquatic habitats. The laws in the other two states are pretty different. Florida started their regulatory regime in 1990, and they call theirs a minimum flow and level requirement. And they want to protect that minimum flow such that it wouldn't significantly harm water resources or the ecology in the area. In California, they talk about protecting a public trust resource, but pretty much only the Sacramento San Joaquin River Delta only. That's the big river system that flows in the San Francisco Bay. So in fact, all of these laws require some concept of a regime, meaning environmental flows with different timing, such as a seasonal flow or wet and dry periods, recognizing the fact that droughts occur, different volumes and in different locations. Now, what happens if we don't take care of environmental flow? Well, we've got a lot of research going back a very long time, and we show that impoundments have many effects. Primarily, it's because the salinity increases, but we also get less nutrient input, less sedimentation, less sediment input, and all of these things lead to loss of habitats and productivity in the coastal zone. A good example is in our backyard. Prior to dam development, the Oasis Basin had 3 rivers that were flowing naturally into the coast, which is Nueces Bay, right outside Corpus Christi at the bottom. And by 1982, we had built 2 reservoirs with over 1 million acre-feet of storage capacity. The problem, of course, is that our average rainfall and runoff in our area is only about 600,000 acre-feet. And of that, half we lose to evaporation every year from the dams and from the bay surfaces. And so this has led to a dramatic change in hydrology of our river and estuary. On the left, you can see prior to dam development, inflow peaked in the spring and in the fall, and it was generally net positive. Now, inflow is more net negative on average, and in the summertime, it can be extremely negative, which means our estuaries become hypersaline. And for example, here's a good example of a flood, of a drought, what the estuaries can look like in a flooding period. And of course, this has led to loss of many species, a lot of productivity. That has led us to do 2 major restoration programs, hydrological restoration programs. And one is we created a ditch. We lowered the bank to increase opportunities for river flow to go into the marshes, which are in the foreground in this picture on the right. This is the river which takes a bend and heads toward Corpus Christi. The second thing we've done is we've literally created a pipeline to pump water from the upstream area behind the saltwater dam, which is just off the screen here, and directly into the marsh. And that enters right about here. So those 2 projects have basically restored the salinity gradient. They've restored habitat use. They've restored the nursery function of the marsh. But we have some new issues because of actually creating false flooding at times. But overall, it's been a rather successful program, and we have been able to, whoops, I was trying to stop sharing my screen. And it shows that even if you have problems, you really can help to solve them. So what I'd like to do now is hand the presentation over to the next speaker, who is David Colon. and he is going to speak on policy strategy and risk assessment of water management.
Thank you, Paul, for presentation. Hello, everybody. Let's start sharing. Do you see my screen?
Yes.
Okay. I try to keep it in. Okay. Okay, let's start. Okay, thank you. So thank you for your invitation. Hello, everybody. Yeah, so first, let me introduce myself. So I'm David Collon. I'm the Director for Public Affairs for Veolia Water Activities and delegate of the French Strategic Committee of the water sector in coordination with the National Council of Industry. The president of this committee is Antoine Fleurot, the chairman of Veolia Group, and the vice president is Béatrice Arbelot from Suez Group. Okay, so this committee represents public operators, local communities, private operators, water plants and network builders, design offices, and innovation ecosystem and clusters. And the aim of this very quick presentation is to share with you first how the industrial water sector in France is organized. Secondly, what are the main challenges we have to face and what are our intervention strategies in the context of climate change, which force us to go faster now. You will find there some figures. We are an industrial sector, so our activities serve four main clients. The first client is the rural and urban populations for drinking water, on water pollution control, on wastewater management, and so on. The second client of this sector is the agriculture. This is a big issue in this climate change context. The third client is the industrial sector, of course, for all the water for processes. And the fourth client, which is often forgotten, is becoming more and more fragile. It's nature. And we recently added this client to our client list. Okay. We therefore gather public contractors, builders of factories on water and sanitation networks, private and public operators, suppliers of equipment for municipal and industrial business, design offices which advises communities, builders, and or operators. We have competitiveness pools too and innovation clusters. We have a national competitiveness cluster. The name is France Water Team, gathering about 300 innovative medium-sized companies. We are funded in, you see the picture here, we are funded in 2017, a French confederation for the whole sector, so-called La Filière Française de l'eau. And this confederation gathers business association and professional federation. And this confederation tried to enlarge the vision of each business segment for tackling the global evolutions, and we try to favoring the public-private dialogue for more equitable and sustainable solutions required by the needed paradigm shift. Okay. I go quick on the figures. You will find here the French sector in the breakdown of our jobs. And we have a very wide range of jobs and qualifications. Like other industries, we have high tensions in the employment of electricians, electromechanicians, shaders, on all jobs related to data treatment or engineering. And I forgot to say that every 2 years, a strategic contract is signed between the French state and the industrialists of the water sector to achieve measurable objectives. So, what are the three main water challenges to face? We have three main challenges. The first one is the infrastructures and asset management issues. The problem is that infrastructure are mainly built after the Second World War, are very old, especially in rural areas, which do not have nowadays the financial means to renew their assets. So they must be replaced, these assets must be replaced, or otherwise management costs will explode. There is many issues linked with the interconnections to water resources between municipalities, and that's the big issues with the hydric stress. We have to evacuate pollutions and pathogens from residential areas, and the COVID crisis showed that very strongly. And we discover new pollutants every day. The regulation on this subject are becoming more and more strict, and the COVID crisis show us or reminded us collectively that the elimination of wastewater is vital for the development of agglomerations. You know that the lack of toilets in informal settlements in poor countries, the shanty towns, has been an aggravating factor for the vulnerability of people in the COVID crisis. So the health issue, we have other issues dealing with rainwater networks to reduce the pollution discharged into the increasingly fragile aquatic environment in rainy weather. And Paul showed us that with his presentation. We have to face some issues in cities linked to the waterproof of the cities and the refreshing subject. To this global plan, we must add investment in research and development on essential claims to water management like blockchain, artificial intelligence, bioconversion, innovative technologies for new pollutants, and so on. Additionally to these three main water challenges, we have some big issues. The first one is how to imagine a chemical transition. And this chemical transition, how can we finance it by avoiding an increase of the water price for the final consumer. For this point, we look at the European taxonomy and other taxonomies to find financial options to face those challenges. So, as you know, we are currently, as you don't know, we are currently working on the creation of a French Research and Innovation Committee, gathering the main public research centers. And the aim is to promote a big partnership and increase the dissemination of mature researches to companies able to selling and developing them. Okay, so it's something we will implement this year. After we have some main technological solutions to face. The water industry will have several changes in the next year due to the rapid urbanization, for severe climate change, rising consumer demands, and the implementation of emerging digital technologies. But the question is still how the industry can turn the challenges we described before into opportunities that benefit businesses, their consumers, and perhaps more importantly, are good for the environment. the water industry is standing in front of huge issues, but there is 4 main points we could highlight. The first one, I said, acting on the increasing effects of extreme weather events. Most climate changes are related to water in one way or another way by affecting agricultural production, sea level rise, Paul said that, wildfires, and so on. And sea level rise and extreme storm will affect coastal areas in a big way. So we have to implement hard engineering structures such as seawalls maybe or dikes to help in some areas, but more sophisticated technologies such as modeling software and simulation can help us to understand the vulnerabilities of on some suggestions on what we have to do. The second issue is the reusing of water in a way of the water footprint of circular economy. You know, in traditional water investment, we go from the river to the water treatment, and from the water treatment to the sewage network, from the sewage network to the wastewater treatment plant, and then to the sea. The issue is to enable new technologies to have a recycling, to have a close flow of water. We call it reuse. Okay? And we have to keep in mind that wastewater contains a great number of variable resources such as nitrogen, phosphorus, energy, and so on. So for the circular economy, it's a good opportunity. We have to protect agricultural production in a context of lack of water. All these issues will challenge water resources. And then we have to implement smart and intelligent network technologies to monitor those issues. I wanted to finish with some indication on our industrial structure. Just this slide to remind you that the French leadership in industrial water management is supported by majors in the sector such as Veolia or Suez Group. These groups have long-term experience in water management and have solid references for dealing with complex or large-scale pollution problems. But in the same time, France has a very rich ecosystem of very innovative small and medium-sized enterprises or companies. They provide solutions in the field of sensors, monitoring and control technologies. They provide technological building blocks for water treatment. And I will cite here 2 areas of excellence for French innovative companies. There is the first one, it's the field of bioassay and bioanalysis. We have brought together under the French France Biosurveillance label, it's a brand, all the players who develop or use tools using living organisms to characterize or treat pollution. Recently, the field of biomimicry has come to enrich our reflection by providing new methods to understand the problems that management solution or technological solution must address. We are thus working with the advice of the CBIOS, the Center for Study and Excellence on Biomimicry, and with the company Mitseco, who is directed by Christelle Roger, who will speak on this forum after me. And Mitseco acts as a project accelerator on our reflections directly in connection with technological approaches or the integration of nature-based solutions for our projects. Okay. And just after those points on the industrial sectors, I wanted to say we never have to forget that we have collectively involved to find and implement solution of those challenges. The challenges for food future with the figures here, the challenges for the cities and industries, how we'll have smart cities in the hydric stress we are facing with. Water energy strategies have to be re-engineered, and the protection of ecosystem is still linked to the water management. All these figures show us how important the way we will be involved in the future we are. Okay. Are you still hearing me?
Okay, thank you, David. Are we going to be doing the question period after each topic, or are we going to wait until both topics are finished right before the break? I can't remember.
Sorry. Yes, as you see, the figures are very impressive because you see it. No.
Yeah.
It works. So, you have them. You see the screen? Oh.
Yeah, I can't remember if we were going to take questions for both of our presentations after each topic, or will we take it on both topics after the break, before the break?
Okay.
We can do after each presentation. Okay. Well, if there are any questions, we'd invite them. You can either turn on your
okay, thank you.
Your voice, or you can just type it in the chat box. It doesn't look like there are any. Well, let's just go ahead and move to the next presentation. And we're actually moving to a new topic now: device sensors and instrumentation systems. And our first presentation will be by Deepak Mishra from the University of Georgia. And he'll be speaking about a cloud-based integrated multi-platform for global observation of harmful algal blooms that engage citizen scientists and monitor aquatic systems health. So Deepak.
Thank you, Paul. Good morning, everybody. Thank you for inviting me to speak at this event. I know it's a long title, but you can think of it as integrated comprehensive system to look at one particular type of event, which is harmful algae or cyanobacterial harmful algae. Before I go into the topic, let me introduce myself. So my name is Deepak Mishra. I'm a faculty member in the Department of Geography at the University of Georgia, Athens. And I am a trained remote sensing researcher who uses satellites and sensors to look at mostly water resources, which includes water quality and wetland ecosystem, wetland carbon, things like that. Most of my research involves, deploying sensor network and developing new type of sensing technologies and linking them to satellites and processing things on cloud. That field has been going through a kind of a transformative change these days with advances in data analytics and cloud-based processing. So what I'm going to do is just give you a very broad balcony level kind of overview of a project that we recently finished, but continuing unfunded and looking for the next round of funding. The project is called CyanoTracker, and it's a project that involves a comprehensive system of citizen science, remote sensing, small scale point-based sensing, water quality analysis, microscopic lab analysis, and put it together in some kind of a cloud-based platform to disseminate it into public very quickly. So so basically, there is a feedback mechanism between these different systems, and I'll talk about that in a second. But first of all, what is cyanobacterial bloom or cyanobacterial harmful algae bloom? So they're mostly a freshwater inland water system phenomena. It's a algae bloom, phytoplankton bloom, that has a dominant species called cyanobacteria. And why we should worry about cyanobacteria? Because sometimes it blooms into a toxin forming bloom. Toxin would be a public health issue. So cyanobacteria blooms are becoming more and more common with changing climate, because one major ingredient that is needed for cyanobacteria bloom to happen is temperature, optimum temperature and optimum nutrient, mostly phosphorus. And both of these factors are available nowadays, more and more. We have increases in temperature and nutrient pollution all over the place. So we have provided anthropogenic drivers, or human-induced climate change has provided optimum kind of environment for the cyanobacteria to proliferate across the world. We're finding cyanobacteria in places that have never been found before. So the ecological effect would be scum formation, light limitations, and eventually leading to fish kills. Public health impact would be the toxins. They contain microcystin, anatoxins, neurotoxins, and hepatotoxins. There are lots of news reports. You can see the toxin impacts on animals and humans and all over the place. And economic effect would be altered taste and odor of drinking water. So shutting down of drinking water, like it happens in Lake Erie time to time, prime example of cyanobacteria blooms. And a serious issue to aquaculture industry. So if there is toxin forming cyanobacteria, then the whole pond of catfish, for example, in Mississippi, they have to be discarded, right? It's a total loss to the farmers, shrimping industry and things like that. So cyanobacteria is a big issue, water quality issue, and there are ways we can track cyanobacteria blooms for large lakes, right? Prime example, Lake Erie, Baltic Sea, or Lake Okeechobee in Florida, Utah Lake in Utah. There are big lakes that traditionally, go through these cyanobacteria blooms every year. And they're big lakes, so there are lots of satellite options available to map them frequently and produce the cyanobacteria phenology, like their year-round growth. But the problem happens when you look at smaller lakes, smaller ponds, smaller system, where the satellite-based remote sensing sometimes difficult because it's a mixed pixel that covers the lake plus a bunch of other things, right? So CyanoTracker is a NSF-funded project from the Computer Science Project Office, part of the CPS project. CPS is a cyber physical system funding program that combines sensor networks, combines social networks, sensor networks, crowdsourcing, advanced remote sensing, and cloud-enabled big data computing. So the entire kitchen sink in there. And the whole idea was to somehow integrate ground-based sensor network for the small lakes and satellite-based remote sensing for the large lakes, and then combine them with crowd sourcing, which is mostly to social media platforms, so that we call it the democratization of sensor network, right? Anybody can trigger the sensor network, anybody can contribute data, and we'll decide how to use that data in a meaningful way to inform people about a cyanobacteria bloom in inland water, right? So early detection lead to early warning, and then early detection also lead to early monitoring, continuous monitoring. So what this does is basically it happens on 3 clouds. One is, so this is the main architecture of CyanoTracker. There is a computational cloud. I say cloud because most of these processes run on the cloud. because that's the best way we can disseminate the results fast, right? Then there is a community cloud, which is the innovation in CyanoTracker, right? Sensor cloud is nothing new. I mean, people have been deploying sensors, collecting cyanobacteria data, because cyanobacteria has a unique characteristic absorption feature at 620 nanometer wavelength, which basically determines whether this is cyanobacteria or a traditional phytoplankton bloom. So sensor satellites have been used traditionally, for cyanobacteria monitoring. But what we did is we combined a community cloud to this sensor cloud. So basically, community input can trigger the sensor, right? And then all this data, the community cloud data and the sensor cloud data goes to this computational cloud, get processed, maps gets prepared, and then it gets disseminated to lake management, water resource managers, ordinary citizens through cloud, social media platforms, and all. So computational cloud, we'll talk about that in a second, but first the social cloud. So we, initially what we used to do is prepare flyers like that, and then we, kind of peppered it through the neighborhood association, because neighborhoods have lakes and golf courses have lakes, and wherever lake management, we traveled all, kind of 400, lake management office in Southeast, distributing these flyers and telling them about our app, which is called CyanoTracker. And so the app is designed in a way it's very basic, because one of the key things about the app is we want people to participate. If we ask them too many questions, then maybe there is a disincentivization right there. So give us a lake name, give us a general location, give us the date, and tell us what you see, and then if you go to a lake. And then, so that's the social side of the things. And then the sensor side of the things, which is sensor cloud, sensors are becoming cheaper, smaller, more plug and play. So we developed a sensor package called CyanoSense. So CyanoSense is a very neatly put together box that we approach a lake owner or a management office and say, can we deploy an optical sensor? So the sensor itself is looking out here to the lake water. And then there is a power budget and the cell phone connection. So whatever data the sensor is collecting is uploaded to the cell phone network. So we get it in the lab, and we can trigger the sensor anytime we want. And we trigger the sensor when satellite is overpassing, and it gives us a very controlled data set so that we can match it with the satellite. We also deploy sensors like these. So this is called Aqua Blinker, which gives you very hard water quality readings like temperature, conductivity, pH, and things like that. And the beauty of this kind of sensor that they just bob around everywhere and then give you a GPS location and then directly transmit the data to satellite. And then you download it in the lab. So if you don't have cell phone coverage in your area because it's a remote location, you can use these options where the data is uploaded to a data transmission communication satellite and then downlinked in the lab, and put them together in a Raspberry Pi Arduino board kind of system, and then deploy it. And then the beauty of this sensing network is that it is connected to the social cloud. So if you go to a lake for a picnic and you see something and you suspect it's cyanobacteria, you can tweet to the CyanoTracker Twitter handle, and then the sensor triggers after some time to basically validate your social media input, whether you are saying something that is true or it's it's a fluke or what, right? It's a noise, because social media is not the most accurate source of information, but we will validate it with your sensor, with our sensor, if the sensor is deployed nearby. So all this data set, the sensor data set, the satellite data set, everything goes to the computational cloud. And we have a ton of algorithms that we have developed over the years that take the sensor data and break it into absorption properties and then spits out a PC, which is the phycocyanin, which is the pigment in cyanobacteria concentration. If you want to know, I know it's super fast, it's a broad overview, but if you want to know more about the details of each of these, you can go to this publication and learn more. So quickly, the last slide, I'll show you some products here. So over the last 4 years, we have mapped cyanobacteria events all over the globe. Wherever we get a report, let's say a lot of people tweet to cyanobacteria, a cyanotracker Twitter handle. We have more than 2,400 followers, 2,500. Among the followers, NASA, European Space Agency, USGS, all of them follow us and we follow them. And if we get a tweet from a foreign location where sensors are not deployed, and if the lake or water system is large enough, then we start tracking based on our satellite models to give them timely information about the cyanobacteria movement around the lake. So we have produced tons of these kind of maps and disseminated it to people. And we have received tweets from all over the place, and you can see the distribution of tweets. We have analyzed tens of thousands of tweets every year, and then the tweets have a seasonal kind of rates coming in the highly in summer. A lot of areas are lacking cyano tweets, maybe lack of awareness in the but we are working on it. We are improving our cell phone app to make it multilingual so that we can have a Spanish version, a Hindi version, maybe a French version someday, so that people can tweet. So how this whole thing operates is once a site is reported through the app or social media and confirmed by the sensor, whether it is a sensor that is located on the lake or it's a sensor that is satellite based, our team starts frequent monitoring and generating daily reports and putting it out there on social media. The report contains, if it is a comprehensive report that has sensing data, then the report will contain a remote sensing spectra, the model estimated concentration, the spatial distribution map if the lake is large, and a date of the initiation of the bloom. And once cyanobacteria is confirmed at a site, a broad-scale spatial monitoring occurs through satellite and drone-based sensing. So it's up to the lake manager then to monitor more frequently. And not all cyanobacteria are toxic, let me say that. So the lake manager or the lake management authority have to do some kind of toxin analysis to be able to see whether this is a toxin or nothing to worry about here. They can post warning signs saying access denied to this lake, or don't let your pets swim in this lake. So there are a couple of interesting things happening now, which is we are working on models to say if there is a, can we predict using deep learning methods, predict toxin from a cyanobacteria data set. So that's one thing, improving our website to have cloud-based processing like Google Earth Engine and things like that so that we can disseminate maps quickly. And then finally improving our app to make it more, more accessible to other foreign countries. So those are the things that's happening. I'm happy to take any questions after all these presentations are over. Thank you.
Well, thanks a lot, Deepak. We actually have quite a few questions for you here in the chat box. One question is, what's the precision and efficiency of the cyno tracker?
So if by precision, if you mean accuracy of the detection, the accuracy of detection actually depends on what kind of sensor is deployed. If it is a small lake, let's say you are talking about a pond and we don't have any sensors deployed near there, then accuracy of course reduces. But if it is a large lake and we can resolve it through satellite data set, our accuracy is more than 80%. And efficiency is also, it's a small team, so we try to get to your lake as soon as we get information. So most likely you'll get a map within 2 days, and then you'll get subsequent maps after that from us. So models are improved continuously as we get more and more data. Nowadays, I'm an optical modeler, so I do optical remote sensing models. But nowadays, the name of the game is machine learning, deep learning based model. So they're getting more and more accurate. So I think it would not be surprising if we go to a 90% accurate detection of cyanobacteria down the road. Hope I answered your question.
Yeah, great. Another question is, can the events be predicted?
Yeah, so we have done some predictive modeling, but that predictive modeling takes us beyond the lake to the watershed. So, to be able to predict, cyanobacteria model, you need to know the watershed composition, the climate variables, the precipitation, temperature, nutrient input through the watershed. So if you have all those data, I have a paper on prediction model for Georgia. I'm happy to share, but there are like 15 or 16 landscape variables that could play a major role in prediction. And one of the key criteria for prediction is the history of toxin-forming cyanobacteria bloom in that water system. So that plays a big role in prediction model. But yeah, we can predict it if the data is available.
Okay, I think we're way behind schedule, so we're going to go ahead and move on to the next speaker.
Okay, just email me if you have any questions. I'm happy to answer those. Thank you.
Just look in the chat box and you can see questions there, and maybe you can type in responses.
Okay, I will.
So the next speaker is Pierre Tuffigo, and he's going to speak about electromagnetic detection, navigation, and characterization systems based on the electric sense technology. So Pierre, can you please show your screen?
Yes. Hello, good morning.
Thank you.
So I'm going to share the screen. Normally it should be okay. It's okay. Do you see the screen? Yeah. Do you see the screen or do you hear me? Yeah. Okay. Okay, so let me start. So I'm Pierre Tuffigo. I'm the founder and the CEO of Elwave. So Elwave is a French company, quite young company. It has been created, funded in 2018. As we are in the Biometrics of Biomimicry session, Elwave, we are developing some subsea sensors. It's an active electromagnetic technology called the active electrolocation. So it's a biomimetics one. Here you have a picture of one fish living in South America, which use this active electrolocation for perceiving its environment. Basically, the active electrolocation is used by the different species of fishes living in Africa and South America, and these fishes live in very muddy waters, very cluttered with branches and etc. And in this complex environment, the vision and the acoustic are quite inefficient. And so the natural evolution has led these fishes to develop and to gain a specific perception mode, so which is an electromagnetics one, and which is adapted to this complex environment. Through a biomimetics approach, Elwave is so developing this kind of active electrolocation technology, we generate, so we install our system on vehicles, subsea vehicles, and we generate an electromagnetic field. And so we create around the vehicle an electromagnetic bubble. So this is what you can see on the different picture. And when an object penetrates in this electromagnetic bubble, it will perturbate the electromagnetic field because the resistivity, the electrical resistivity of the object is different than the salt water or the water. And so we measure the modulations, so the amplitude modulation and the phases modulation of the electromagnetic field that we have generated. And with some specific algorithms, we are able to detect, to locate, and to characterize the object which has modified the electromagnetic field. So we categorize the object that we have detected, and we say if the object is spherical or cylindrical or more plane object. And so we do, and we also define, characterize the size of the object. And so this perception, electromagnetic perception mode, we deliver this information in real time and in 360 degrees. The electromagnetic fields propagate all around the vehicles. So we obtain this electrical image in real time and all around the vehicle. So here you have a picture of the casing, and in this casing you have all the electronics, the embedded electronics, and the embedded algorithms. And so this is part of the system which is installed on the vehicle. So it can be some ROVs, it can be some AUVs, so autonomous underwater vehicles. And linked to this casing, there are some electrodes which are placed on different locations of the vehicles. And so these electrodes are used to create the electromagnetic field. Elwave is the only company in the world to develop this kind of systems. And especially it is of high interest for the AUVs. And so Elwave is a French company. So in Europe, you have the European Green Deal, which is the program of the European Commission. I would say a large roadmap in the next years, 10, 20 years. And so we are supported by the European Commission, so in the framework of this Green Deal. And what we do is of high interest, especially for the AUVs, and to give the AUVs a large autonomy and to give them the ability to detect the obstacles, to detect the buried object. And so thanks to the AUVs, the use of the AUVs will largely reduce the cost of operation, so of offshore operations. And so we are supported by the European Commission because of our capability to enable this large-scale deployment of the AUVs. And so we have different application of our sensors. So we have some environmental application. We are able to detect metallic and non-metallic objects. So we are able to detect the plastics. We are able to detect the UXOs, so the unexploded ordnance, the mines of the Second World War, which are largely present in the European seas. And especially some of these UXOs are now buried, and it's extremely complicated to detect these buried objects. And as the electromagnetic field penetrates in the seabed, then we have a good perception of this buried object. We're also able to detect and to locate and to characterize the pipelines, the cables, especially the telecommunication cables, and this is quite of some strategic assets, capability to detect these cables. So this is something that we are able to do. And then we have a strong economical impact too. The European Commission has calculated that the large deployment of the AUVs for the inspection of the offshore wind farm will lead to roughly 500 million euros per year of cost reduction using the AUV instead of the ROVs. And so our capability to enable the large deployment of the AUVs lead to the strong cost reduction. There is, it's not specified this here, but there are also some scientific and oceanographic aspects, and especially the knowledge of the ocean floors. So you have some very scientific needs. There's some economic issues too regarding the deep sea mining. So we have the capability to quantify and to precisely know and define, characterize the ocean floors. So we have several applications: the ROV and the AUV navigation, the buried object survey, as I explained. In a midterm, we have also the capability to monitor the marine infrastructure, especially the corrosion, because the corroded metal has an electrical resistivity different than the non-corroded one. So we have the ability to detect and to characterize the corrosion, but also the biofouling and this kind of things. So we work with several very well-known industrials in the subsea domain, and we are supported by the French and European public agencies. Thank you.
Okay, thank you, Pierre. Are there any questions or comments? Okay, I'll tell you what, we're a little bit beyond our break time. Why don't we go ahead and take a short break and reconvene at about 10:15. That'll only be 5 minutes late. Okay, we'll see you in a bit.
Renaud, I think we cannot have the sound of a natural feature. Renaud, the video is without sound. I think we cannot have sound. Renaud, sorry. Renaud, je crois qu'il y avait un problème de son.
Moi, je l'entendais bien, mais j'ai pas eu de commentaire de retour.
En fait, il n'y avait pas. En fait, il y avait pas. Mais parce que les gens ont dû partir et lâcher leur poste. Mais je pense qu'il y avait pas. Enfin, moi, j'entendais pas du tout le son de la vidéo.
Your screen sharing is paused. Tiens, c'est bizarre.
Là, si tu la remets, peut-être en essayant, je vais te dire si j'entends.
Je la remets.
Mais il n'y a pas de son là.
Alors, le son est faible là, mais ça devrait arriver en fait. Là, c'est bon?
Non, il n'y a pas de son.
C'est étrange. Moi, j'y suis. J'ai du son partout.
Non. Bah, je ne sais pas si les autres en ont, mais moi, j'entends pas du tout. Non.
Ok. Bon, on s'entend. Là, on est dans la pause. Je peux essayer de redémarrer l'affaire, mais normalement.
Non, bah écoute. Non.
Non.
Non. Bon, bah, c'est pas grave. Hein.
Bizarre. Moi, j'ai le son, mais bon, c'est moi qui le génère, donc c'est peut-être plus facile.
Bon. Écoute, on l'a pas. Ok.
Je peux les mettre dans le chat. Je vais les mettre
je
dans
l'ai
le chat.
écrit dans le chat.
Tu l'as mis?
Ouais, qu'il n'y avait pas de son.
Non, mais je veux dire le lien, que les gens puissent.
Ah, le lien. Bah, alors, le lien en anglais, c'est toi qui l'as reçu.
Oui, bah, je vais aller le chercher, puis je vais le.
Ouais, je pense.
Ok, alors attends, je vais aller l'attraper.
On est plutôt en retard, non? Là, c'est bon, on n'est pas en retard. En fait.
Ça va. Je vais essayer de. On devrait pas tarder à reprendre. Je vais mettre dans le chat à tout le monde ce petit.
D'accord.
Okay, I guess we'll be ready to get started in a few minutes. In a minute.
Okay. So Chris. Okay. Hi, Chris. Can you just screen share, please, before we start? Bonjour, Philippe. Can you also share your screen just before we restart the session? Resume the session. Okay.
Can you see me?
We can see the screen.
Okay.
Okay, now we see you. Good.
Hello. Good morning, good afternoon.
Hello. Bonjour, Philippe.
Bonjour. Ça va?
Ça va. Un petit peu de partager l'écran, s'il te plaît, pour...
Yes.
Ça, c'est plus rapide. Tu vas chercher directement ta présentation.
Let me... Okay, should work. Do you see something?
Yes.
That's good.
Good.
And if I share my screen.
And then diaporama. Ouais.
Let me check if it works.
Ah. Tu sais ces diaporamas? Ouais, ok.
No.
Après,
Not
voilà,
this one.
là tu mets diaporama, oui, en haut, en bas, c'est bon. Voilà.
Can you see it?
Okay.
Do you see
For me.
the?
Yes. Okay.
I stop to share my screen, I guess.
Okay, now you can stop, yeah. Okay, thank you. And I would like to see Chris. Can you do the same, please?
Okay.
Okay, and go to your, yeah, and just, okay. And then you have to put, you know, slideshow or the button on the bottom right.
Yes.
Yes. Okay, good. Looks good. Excellent. So for the sake of time, I think it's time to resume the session. And so Paul, the floor is yours. Okay.
Thank you again. So the third topic we're going to be talking about is coastal conservation and water treatment. And our first presentation is by Michael Wetz. He's also here at the Harte Research Institute. And we'll be speaking about, and Chris, could you unshare your screen so Mike can share his? Mike's talk is Citizen Science as a tool to support coastal conservation restoration efforts. And let's all try and stay on time. So Mike, can you please share your screen?
Yes. Am I good?
Good.
Okay, well, I'd like to start off by thanking the organizers for the invitation to speak today. And Paul, to your point, I'm very much a rule follower, so I would definitely keep this to 5 minutes or less. The focus of my talk today will be on the incorporation of citizen science into coastal restoration and conservation efforts. And I based my talk on a very rewarding experience that I had where I worked with a group of citizen scientists to understand why we were having poor water quality conditions in an iconic Texas coastal bay, which is known as Baffin Bay. So in the short time that I have, I'll show you a video that documents our citizen scientists in action. And then I'll briefly highlight a few of the many benefits of working with the citizen scientists. So without further delay, let me show the video first. Well, we were approached by a number of citizens from the Baffin Bay area a few years ago about concerns they had over water quality, fisheries. And so we're trying to figure out what's changed in the system. What are some of the things that might be contributing to the water quality? Well, we've just completed the first year and we have some very interesting findings. And we're starting to really understand how Baffin Bay works from an environmental standpoint. And this has led to some interesting partnerships looking at fisheries. And all of this, though, was really, it really could have been done without the help of the volunteers as well as our funding partners. So all of that's really appreciated. I think it's going to contribute to a much better understanding of what's going on in Baffin Bay. So what that video basically showed is the group of about, so we had a group of about 15 citizen scientists that started working with us in 2013 to collect water quality data that we needed to understand what was happening in Baffin Bay. And so now we're in our 8th year of sampling in this system. I'm really starting to get a handle on what's going on down there. And we're actually starting to work towards some solutions for fixing the problems. And what I briefly wanted to end my talk with is just highlighting a few of the benefits of working with citizen scientists. So in this specific example, but also this is common across a lot of citizen science programs, working with these citizens, it really increased our ability to collect data from a lot of different locations and also more frequently than we could have otherwise without their help. It also lowered the cost for us. So in this example, we had a couple of groups that provided boats and took us out on the water whenever we needed to. And so it helped us, again, to just really get more of the data to better understand the problem. And then also through the participation and engagement of the citizen scientists, but also their network of friends and co-workers, it really helped us to spread the word in terms of, it helped us get the word out there about the issues in Baffin Bay and helped to create better buy-in from the public in terms of implementing some of the solutions that we have down there. But it also benefited us as well, because a lot of these folks have been either living around or working in Baffin Bay for many, many years. So they were a wealth of knowledge about changes in the bay. And it actually helped us to design some additional research projects down there to better understand the system. So in closing, I just really want to point out that there are a lot of different ways that citizen scientists can be incorporated into our science. We saw an example earlier with the HAB project, but there are a lot of great examples out there right now of citizen scientist projects that are having a meaningful contribution towards conservation and restoration efforts. And I really encourage the folks on this webinar to consider this in future projects. It's just, for me, it was just a really incredibly rewarding experience working with these people. So with that, I kept it under 5 minutes, I think.
Good. Thank you, Mike. Any questions for Mike?
Yes, can I ask a question? Thank you. I just wanted to know exactly what is the definition for a citizen scientist for you.
Well, there are many different ways that we can incorporate citizen scientists. Some of them are much more hands-on. Others are playing a more passive role. But for me, it's just bringing in members of the community and other interested folks to engage in the science that we do on a regular basis. And I don't know if that fully answers your question, but I can certainly
I mean,
more offline.
Well, I mean, you do not need any PhD or diploma for being a citizen scientist. You need just to participate to this program, I guess.
That is correct.
Okay.
Yeah, there are different levels of skill, but what we did in this case is we implemented a very rigorous training program up front so that we could be confident that the data they were collecting was something that we could actually use.
Thanks.
Okay, there's one more question, Mike. What about the role of citizen scientists in restoration?
Yeah, well, we certainly have some great examples locally, and Paul, you're very familiar with this one, the oyster reef restoration that happens down here in Texas. There's a very successful program called Sink Your Shucks, where they actually take discarded oyster shells and use them to build new reefs. And so that program has been going on for many years here in Texas and has been wildly successful, but I'm sure there are many other examples worldwide, and you could probably just do a web search to find examples of successful citizen scientists' involvement in restoration efforts.
Okay, thank you. Well, let's go ahead and move on to the next speaker, who is Chris Zachary. He's going to talk about constructed wetlands as a large-scale water treatment strategy. Chris, can you share your screen? Looks good.
Okay, can you hear me just fine?
Yes.
Excellent. So yeah, I would like to introduce a project that we're very proud of here at Tarrant Regional Water District. So visit with you a little bit about who we are and what we do. Tarrant Regional Water District is a large raw water supplier in north central Texas. We provide approximately 2.5 million gallons a day to the North Texas area. And I misspoke, sorry. We provide 350 million gallons a day to 2.5 million people in the North Texas area. The North Texas area is rapidly expanding. We expect that population to exceed 3.5 million by 2050. And to meet those increasing water supply demands, the water district was looking for ways to incorporate reuse into its water supply portfolio. We started working on this technology in the 90s and went through a series of pilot scale, field scale, and then full scale implementation of the project, which was completed in 2013. So the wetland system that you can see here consists of 2,022 acres. We have actually 1,730 acres of marsh. And the removals that we can achieve through this process of the nutrients from the reuse water is in the magnitude of 85% sediment removal. We can do 55% of the total phosphorus and about 75% of the nitrogen that is in the system. The goal of this project is to treat the water to as good or better than the receiving tributaries for our reservoir systems. And you can see here in the photo, this is the actual, a small picture of the actual discharge where we pump the water back to the reservoir. Next slide here, it'll go. This is a little bit about the reuse cycle and how it works for us in our system. So we own Richland Chambers Reservoir. It was constructed in the 80s. And we have a 90-inch pipeline that delivers water to Tarrant County. It's approximately 90 miles away. So we deliver the water to our customers in Tarrant County. They treat the water and then deliver it to the cities where people use it for, in their households commercially, and then deliver that water back to the wastewater plants. And once it leaves the wastewater plants, it's discharged into the Trinity River Basin at various points. And so we've constructed our project. It's about 110 miles downstream on the Trinity, next to Richland Chambers Reservoir, where we relift that water from the Trinity, put it into our wetland system, and then divert it back into our reservoir. So it completes a full cycle. So there's quite a few benefits for us with constructed wetlands. It's very dependable water supply in times of drought. In the North Texas area, rain is very unpredictable. It seems like we either have too much or too little. But in times of drought, it's really by utilizing the reuse water that's coming from the wastewater plant, it's a dependable source that we can put back into our systems and use. And so that was really appealing. The wetlands provides a tremendous amount of habitat, for a variety of plants and animals. There's actually public use on the project. It's utilized for hunting land and other studies by a variety of universities in the state of Texas and Louisiana. one thing that we really tried to minimize is the impacts on bottomland hardwoods, and reservoir construction typically consumes large amounts of bottomland hardwoods and biological corridors for wildlife, and our wetland systems and the recycling ability of them can be constructed on a much smaller footprint on lands that were historically used for agriculture purposes. And so they're for the yield of water that we can use from them, and they're about 1/20th the size. And so you know, it's a win-win for the environment, it's a win-win for the communities. You know, the people benefit, and you know, at the end of the day, they're much more cost effective to construct, operate, and deliver water for our customers than building surface water reservoirs. So I'd like to just close with just we're really proud of this innovative technology that we've utilized in our systems, and be glad to ask any questions anybody have about the project.
Thank you, Chris. Do we have some questions for him? Oh, here we got one. Do constructed wetlands reduce or eliminate the need for another reservoir, or is it more of a supplement?
So we have 4 different reservoirs that are in the planning stages between now and 2080. Most of our planning is 50 years out. So to answer your question, yes, it does move those projects further out in the future. There's only so much reuse in our system that we can utilize. And to that, we're currently in design phase of a sister project, which is the Cedar Creek Wetland Project, and it will be delivering 81 million gallons a day to that reservoir that we own, and providing that water back to our customers in the North Texas area.
And one more question, Chris. How long does it take to treat the river water in a wetland system?
So from start to finish, it's approximately 7-day detention time, and it varies depending on you know, how much water we're flowing through the system, but 7 days.
Great. Well, thanks a lot. We'll move on to our next speaker. So if you can unshare, Chris. Our next speaker is Mihail Barbu, and he is going to speak about artificial water channels toward a biomimetic membranes for desalination. You're all set. Go ahead.
Thank you, Paul. Thank you, everyone, for inviting me here. It's a nice pleasure to be with you today. And good morning in US. Good afternoon here in France. I'm Mihail Barboiu. I'm the senior researcher at the Institute European of Membrane in Montpellier, in the south of France. And as I would like to introduce you a little bit of field we are dealing since 10 years. And as most of you know, that desalination is a very important process in order to produce drinking water, or and for this reason, many people, they are using membranes. Besides the use in membrane distillation, which is highly energetical demanding, or using the reverse osmosis membranes, desalination is trying to do the ultimate separate projects, doing the separation between water and ions. We have introduced many years ago the concept of artificial water channels, which are meaning the synthetic conduits that transport water selectively against ions. Then after we characterize these systems, it is highly important to introduce them into the membrane, then to show it recently that it's possible to get important advancements in the production and the performances of desalination membranes. water transport through a cell membrane, if we are speaking about biomimicry today, is done in the cell membrane by aquaporins. And in fact, from these aquaporins, there is a story of confinement, interaction, and selective transport of water. As these proteins, they can transport billions of molecules of water per second with an extraordinary performance, 100% ion exclusion. They have been used by now by the people and included them into the membrane with a hope to improve the performance of desalination membranes, notably in the permeance of water and keeping very nice selectivity against ions. They are very well working in different fields, and there are many companies around the world doing this. But one important thing is that this kind of systems that cannot be adapted to all the time to the very harsh conditions in desalination, like high pressure or high salinity. So a possible alternative to do this is to try to build artificial constructs by using simple and very easy synthesizable molecules. And we have discovered this 10 years ago, in which different kinds of sub-assembly molecules can be used in order to create very similar structure to the aquaporins. We call this artificial water channels, and they were very highly competitive to the aquaporins in terms that the molecules can transport billions of molecules per channel and per second of water, with a very high selectivity, doing what we call angstrom scale separations. Because normally now the idea, and to have to go to a very nice paradox, is to try to use this angstrom scale separation constructed at the biomimetic level, and to build right now square meters of membranes. We have done this very recently, and we find the possibility to embed these channels in the classical polyamide networks membranes, presenting larger voids into the membrane and incorporating in a very homogeneous way our I-quartet channels into the membranes. These membranes, they are doing very well in a sense that they are transporting, first of all, 3 times more water than the same reference without artificial water channels. And they are also right now performing twice better, if you want, double better than actual commercial membranes under the market. Because of we adopted a very specific strategy in order to get a very homogeneous introduction, a biometric introduction of the channels within the system. They show exceptional mechanical resistance, where they are chemically robust, and they show this real improving of the flux and the productivity, which for sure they will imply very interesting things, as the membrane is not costing very much into the system, but what is inducing is, for example, like reduce the pretreatment costs, which are huge in such processes. We have calculating, and in principle we can get an important reducing cost of the desalination process by reducing the energy. At the moment only 12%, but the process could induce more for this. And another major evolution is also that the new generated membranes we can engineer if you want reduced installation with reduced dimension, which will improve a lot the capex investigation cost into the system. I'm finished. I hope I convince you a little bit. I will be happy to take some question about the field and to give you more details during the next minutes. Thank you.
Thank you. Do we have any questions from Mayo?
Can I ask a question?
Sure.
Yeah, is there any selectivity depending on the ion using your membrane? Like you can.
Yes, our membrane show 99.6, 99.9 selectivity for sodium chloride. Mm-hmm. And we have 94, the most important equipment, 94% rejection for the boron. And also for calcium and magnesium sulfate, which are classically much better than sodium chloride into the field. So we have very nice, more than 99.5 selectivity for each ion into the system, because we have tested these membranes by using standard seawater conditions, if you want. Exactly, natural models for seawater and also real seawater into the system.
And how can you explain this selectivity? I mean, is it a question of size?
The selectivity in these membranes, we generate specific hybrid structure between the polyamide and the water channels. The water channels are more or less like 1 million molecules per second and per channel. And when they are introduced into the membranes, you have to count that in principle, the permeability when the water is arriving in this region is something like we calculated 500 more permeability than in a regular polyamide matrix into the system. And this is a reason I think we're introducing some water facilitators transport into the membrane, and this is very important in terms of increasing the permeability. But attention, you have to pick to keep up the selectivity, and you get the right point at the beginning of the question.
So balance
without any selectivity, and these channels they are highly selective. That is highly important, and we have to build the membranes in this way to keep the selectivity and increasing the permeability into the system. And I think the biomimicry can do this.
Thank you. Thank you.
And
fully agree.
Is this technology being used anywhere to scale to provide actual?
Right now we are constructing the pre-industrial prototypes. Because normally in the lab we can prepare more or less A3, A4 formats for the membrane. Right now we are doing square meters of the membrane, and we are doing the pre-industrial stuff to do 2-point-inch cartridges for desalination. And thus by the end of the year, I think we will be able to do the pre-industrial scale, and then with this one, I think we can go forward to the industrial scale and the membrane preparation. The idea is absolutely clear. We have to prepare 100 or square meter of membranes. Now we are more or less in the level of tens of square meter of membranes, and we are very confident because the technology is starting to go very well in the field.
And do you have industrial partners?
Yes, we have a very, very competitive one now helping us to do things.
And one last question: how long? What's the lifespan of these membranes? How long do they last?
Yeah, this is highly important. The membrane in general must be robust. That's for sure. Get a marriage between the polyamide membranes and other systems like zeolites or particles or whatever. These membranes must resist to the harsh condition of desalination. Specifically 60 bars of pressure, and when the membranes can change the structure very easily. In our case, the specific generation of the hybrid structure with the in situ generation of the water channels, this is getting something which is very stable. And for the more lifespan, if you want to more or less, right now we have tested during months, and also we have tested by using the classical basic and acidic conditions, chlorine conditions, if you want, at a specific concentration. For the polyamide, they are not stable. Also, the chlorine they are not stable, but doesn't matter. They are not stable. The polyamide is not stable, but using the specific condition, these membranes are stable during months.
Great. Okay, well, thank you very much. I think we'll move on to the next speaker.
Thank you very much.
The next speaker is Philippe Barthelemy. He will talk about biomimicry as a strategy for water decontamination. And I can see you're sharing your screen. Go ahead, Philippe.
Thank you. Can you see my screen? Yes. Okay.
Yes, well, we're seeing the presentation view.
La diapo qui va suivre.
Can you see it now?
Okay. Good.
Okay. Thanks. First of all, thank you for the invitation. I'm very happy actually to be part of this great event, and thank you for this invitation. So I am Philippe Barthelemy, professor at the University of Bordeaux in the southwest of France, which is not next to Montpellier, it's another city. I am director of the ARNA laboratory, which is a lab working on nucleic acid biology, chemistry. But today I'm not going to speak about nucleic acid. I'm gonna share with you some a new technology, new way of maybe using new technology for decontamination. So we're gonna do a sort of biomimicry as a new strategy for water decontamination. So what is the exact context? At least you can have two different family of pollutants. The first family is linked to nanoparticles. We call that nanopollution or nanopollutants. And for this family, you can have different sources of nanomaterials, including nanoparticles coming from laboratories or biomedical activities. So you can find silver nanoparticles or metal, therapeutic metal nanoparticles. So any kind of nanomaterials which can be useful for therapeutic application or bioimaging, but also some nanoparticles coming from industry, transportation, wastewater, coming from domestic wastewater. And so at the end of the day, all those nanoparticles go to the environment. So you can have nanoparticles in the air, soil, or even in aquatic systems. So for this particular system, I mean, it's really important to look at the aggregation of nanoparticles, deposition, but also some of the nanoparticles can be stable in water and suspension. And so you can have long distance transportation, meaning that you can have a large pollution of those nanoparticles. So most of the nanoparticles cannot be well treated right now by wastewater treatment plants. So the second family, at least is also the organic pollutants. Some of them are coming from pharmaceutical drugs. And so as it is shown on this slide, more than 90% of drug can go to wastewater. So most of them cannot be well treated as for the nanopollutants or nanoparticles, and you can find some residues in drinking water in some cases, which is not something you like. So the question is, can we take advantage or inspiration from nature in order to address this particular issue? So before to show you this movie, we thought that maybe we could look at a very old animal, a jellyfish, and use this animal for trapping nanoparticles. So to make a long story short, I mean, we started a project more than 10 years ago on, thanks to the funding of coming from the French National Research Agency, the ANR, on a project on bioimaging using nanoparticles, some quantum dots. I don't know if you are familiar with those nanoparticles. And in one of the work package, we look at the toxicity and the impact on the environment, the nano-ecotoxicity of nanoparticles. And so we discovered that that those nanoparticles were quite toxic actually in many different models, including one using frog eggs. And we also discovered, which was very, very interesting, that the jelly material wrapping the frog eggs was able to trap actually the nanoparticles. So we decided to investigate a jellyfish in order to use the jelly material, the mesoglea of a jellyfish, for trapping the nanoparticles. Unfortunately, this material was not able to trap the nanoparticles, but the mucus secreted or generated by the jellyfish were able to trap the nanoparticles. As you can see on this simple drawing here, so here is a sample with a contamination of nanoparticles, which can be positively charged nanoparticle or negatively charged. I mean, you can have different zeta potential of nanoparticles, and thanks to the mucus, you can trap those particles into a network and remove all the nanoparticles from the contaminated solution. So that's really interesting because, as you know, it's very difficult to actually filter the nanoparticles because they are too small. So here is a movie showing the very simple technology. This guy is a part of a consortium Fabien Lombard, he goes to his lab after fishing some jellyfish. This is a jellyfish which is a pelagia. And by just stressing the jellyfish, as you can see on the movie here, the jellyfish is going to make some mucus, some jelly and sticky material. In parallel, this guy is preparing some nanoparticle samples using gold nanoparticles. That's the reason why you can see the pink color of the solution due to the presence of nanoparticle. And then he is going to get the mucus. So you're going to see how the sticky material coming out from the jellyfish. And then you pour the mucus, you insert the mucus into the contaminated sample, and you can just stir the sample, stirring the mixture, and you're going to see that spontaneously all the nanoparticles are trapped inside the jellyfish mucus. That's very efficient and very simple method in order to trap nanoparticles. And I have to tell you that it's almost impossible to remove all those nanoparticles using a simple filter. So this is before and after using the jellyfish material. So it's very, very efficient. So then, thanks to this first approach, since we are chemists, we can do a sort of biomimicry of the material. We did an analysis of the mucus material, and we discovered that this material is made of N and O glycans. So we made the amphiphilic molecule featuring sugar moiety, and we can form an artificial supramolecular gel. And as for the mucus, this supramolecular gel, which is pure artificial gel, can capture and trap all the nanoparticles, as you can see on this electronic microscopic image. The nanoparticles are right there, as you can see, trapped inside the network. So here again, this is before and after. You can remove 100% of the material. I'm going to end this presentation with the other decontamination. Here we do a biomimicry at the molecular level to remove the pollutants, the organic pollutants. Here we use, if you're a chemist, you can recognize the nucleotide or nucleoside molecule, which are present in nucleic acid molecules, biomolecules, like in DNA or RNA molecule. And we know that those molecules are very well known for their weak interactions with the different partners. So we decided to take advantage of those weak interactions in order to induce some interactions between the molecule and the pollutants. So as a first series of experiment, we used propranolol or diclofenac, which are well known to be an issue for wastewater plants. Actually, it's really difficult to remove 100% of those molecules. And by using a little bit of those materials, simply just by pouring the solid material at the surface of water, you get an aggregation thanks to weak interactions with the pollutants. You get aggregates, and you can filter those larger aggregates. So as you can see here on this part of the slide, we can remove 100%, almost 100% of the propranolol and the diclofenac using this technology, whereas using a simple filter, you cannot remove anything from water. Also, we finally did an experiment using a cocktail made of different pollutants, including drugs, but also pesticide. And here again, by using our technology, we can remove almost 100% of the material. So the message here is obviously we can get bio-inspiration from nature in order to solve very important issues such as the pollution. So thank you for your attention, and I would be happy to answer to your question. Thanks.
Very, very fascinating. So how big, how much of volume water can you treat using this process?
Well, we have done, it depends on the nanoparticle site, I would say. I mean, we treated liters of water right now. We did an experiment only on liters. So but we can scale up the system. I think that's something we need to do to carry on that particular project. The point is you need to have enough jellyfish to produce mucus. So, and I mean, something kind of tricky, I mean, to have a large amount of jellyfish.
Yeah, that leads to the obvious question: can you build jellyfish mucus artificially? Have you characterized the chemical structure?
Well, yeah. We characterize actually the structure. It's very complex molecules. So as I mentioned before, yeah, very, very complex molecule. It's an oligosaccharide, a complex oligosaccharide linked to lipids, and so we made a very simple analog, which is quite easy to make, and which is almost as efficient as the jellyfish mucus, mimicking actually the structure, the sugar structure.
Right. Yeah, it's interesting whether this could be applied elsewhere in the world. And one of the interesting things is, as it's actually a consequence of fishing pressure all over the world, as well as nutrient addition to the oceans. We're seeing shifts where the plankton is being more dominated by jellyfish rather than zooplankton. And so these kinds of jellyfish species are everywhere, and they seem to be increasing in abundance worldwide right now. So this would have an application really globally, wouldn't it?
Yeah, I fully agree. Actually, at the beginning of the project, it was a double objective. I mean, solve the jellyfish bloom and at the same time the pollution. So we are very ambitious,
Yeah, I love the idea of taking a problem and turning it into a solution.
Exactly.
Okay. It looks like we covered all of the questions that are in the chat box.
Thank you.
It sounds like you're still pretty far away from moving into some industrial scale, though, aren't you?
No. We are still working on the scale up. I mean, this is the next step. We have several patents on it, on that particular project, but we carry on.
And what about, one more question, what about other pollutants beyond nanoparticles?
Well, that's actually the case, as you can see on this slide, using
organics.
Organic pollutants, using some biomolecules. So here is an example. We can remove, it's not exactly the same technology, but first I have to confess that we try to use the jellyfish mucus to remove all the organic pollutants, but it doesn't work very well. So the efficiency in removing is only a few %. So we decided to move to another kind of decontamination system in parallel to the mucus.
Right. There is one more question that's kind of interesting, and that is, would you have to treat this over a large area, or is it just a volume? What's the most efficient way to expose water to the jellyfish mucus?
Oh, you mean depending on the type of sample?
Yeah.
Well, no. It's I mean the volume. I mean we can treat a volume, is not a surface. I mean it's I don't know if I answer correctly to the question, but it's a volume question. It's not a surface. It's not because you are putting a large surface that you are going to increase the efficiency in removing the nanoparticles. It's a volume.